Hello, in this video we are going to see about finite automaton. So finite automaton is the least model in the Chomsky hierarchy which has the lowest power when compared to the other mathematical model. We have already discussed about the Chomsky hierarchy of languages and the equivalent mathematical model. So here we are going to introduce the finite automata, which is the first mathematical model which we are going to discuss in our syllabus. So finite automata is a mathematical model that is used for recognizing patterns from the given input taken from a character set. So normally all mathematical models usually is used for recognizing a pattern that is a particular language. So a unique feature of the finite automaton is that it is a memoryless model. It means that it cannot remember anything. Hence, the computational power of this mathematical model is restricted. The language accepted by this finite automaton is known as regular language. For example, the pattern say 101110 in the binary input, that is we are here taking the input alphabet as 0, 1. It can be verified using by constructing a finite automaton. So later, after discussing deterministic finite automaton and NFA, we'll see how this memoryless component of the finite automaton restricts its computational capability. So normally a finite automaton consists of set of states and transitions as shown here. So here the circle represents these states and the transitions are represented by the arrow mark. So it is unidirectional. It means that from A we make a move from the state A to the state B. So finite automaton are represented with the help of this states and transitions. So there are two types of states here. One is the starting state and another one is the accepting state. And the starting state we represent using arrow mark, while the accepting state is uniquely identified with the help of the double circle. So normally a transition starts from the starting state and ends with the accepting state. So there are two types of finite automaton. One is the deterministic finite automaton and another one is non-deterministic finite automaton. So deterministic finite automaton. So in deterministic finite automaton, every state in the automaton has exactly only one transition for an input symbol. For example, here when we observe this transition diagram, it is understood that A is the starting state while the state C is the accepting state. We have a transition from state A to B on the input symbol 0. Similarly, there is a transition from state B to C on the input symbol C. So from state C on the input symbol 0, there is a self transition. It means that it starts from C and ends in C. So when we observe this diagram, there is exactly only one transition for the input symbol 0 from every state of the automaton. When this property gets satisfied, we call that finite automaton as a deterministic finite automaton. So while in case of non-deterministic finite automata, every state in the automaton can have more than one transition for an input symbol. It means that see, when we observe the state A, for the input symbol 0, we have two transitions. One transition starts from A and ends in the state A itself, while the other transition starts from A and ends in the state B. So if an automaton consists of more than one transition for the same input symbol, so that more than one transition must be for the same input symbol. If I have more than one transition from a state for two different input symbols, then I cannot consider that as a non-deterministic finite automaton. When I have two different transitions, that is more than one transition, it can be even 3 or 4 and so on, for the same input symbol from a particular state, then we call that finite automaton as a non-deterministic finite automaton. See, among the deterministic finite automaton and non-deterministic finite automaton, usually with respect to computer science point of view, we prefer deterministic finite automaton because always we try to pass a deterministic algorithm for any computer. So whatever is given or but non-deterministic finite automaton is easy for me to construct because I don't have a restriction that for every input symbol there should be exactly one transition, there should be a transition. So those kind of restrictions are absent in case of non-deterministic finite automaton. So these automatons, whatever it may be, whether it is a deterministic finite automaton or a non-deterministic finite automaton, there are two ways to represent. One is the transition diagram representation and another one is the transition table representation. See, whatever we have, the representation which we discussed in the earlier slide is known as the transition diagram representation. Hence, the transition diagram representation consists of a state and the transition. It means that the circles and the edges. So the other representation is the transition table representation. So in transition table representation, we'll construct a table. So the number of columns in the table is equivalent to the number of input symbols present in the automaton. In the example that we have taken, there is only one input symbol, say 0. So this table consists of only one column. So the number of rows in the table is equivalent to the number of states that is present in the automaton. So here in our example, we have three states, namely A, B and C. Hence we have three rows. And in case of transition diagram, we represent the starting state with an arrow mark and an accepting state by double circle. In case of transition table representation, we represent the starting state by an arrow mark, same as that of the transition diagram. But we represent the accepting state with the help of a star symbol. So either I can go with transition diagram or a transition table notation, whichever is convenient for me.